In the last video, we introduced the concept of electric potential energy, and we found an expression for the electric potential energy of an object in a uniform electric field. We also presented the results for the electric potential energy for two charges, but didn't yet prove it. So we're going to go back and visit that here. So we can assume that both charges are positive, and then all the signs, if the signs aren't both positive, they'll be taken care of automatically in the expressions. So we can just do everything as if it were positive. So what I'm drawing here now is just the electric field for our charge A over here. And remember, so first off, we need to establish, is the electric force even conservative? We saw that definitely was in the case of a uniform field, but let's go take a look at it here. So remember, the definition of a electric force, of any force being conservative, is that the work done by the force winds up only depending on the endpoints and does not care about the path that connects the points. So what you need to be able to show is that for every possible path, let's not make it quite that squiggly. For every possible path, I'll try it one more time. Oops. For every possible path, yeah, we'll do that one, sure. For every possible path that connects your beginning and your ending point, you will get the same answer for the work done by the electric force. So let's go and take a look at that. So the trick here is exactly the same trick that we did for gravity, which is what we imagine replacing this path with a combination of circular arcs centered on the charge, along with line segments that are directed towards the charge. And we will just sort of zigzag our way along, kind of like something like this. And then maybe it goes back in like that, something like that. And the first step we have to take a look at is, well, how much work did the electric force do here? Well, the displacement here is going to, say dr, is going to be perpendicular to the electric force, because keep in mind it's a positive charge. The electric force will be in the same direction as the electric field. So that's perpendicular. So along this circular arc segment, the work done by the electric force is 0. And that's true for every one of these circular arc segments. And here, along these segments, it's just going to depend on the initial and the final radius. The dot product will, because the force and the displacement are collinear. So this means that it doesn't really matter what path we take. And if you object that this pink path doesn't look like the blue path, you can always make the zigzags finer and finer and finer until literally the differences are less than a pixel. And mathematicians have proven that you can rigorously do this. It's much like the trick that your calc professor probably did when they started looking at curves and approximating them by a stair-step collection of vertical and horizontal lines. But anyway, the result here is that since this sideways motion doesn't matter, and all that matters is the radial motion, we can conceptually replace this with just one path. That one. So along this arc, the work done will be 0, and here the work done by the electric force is not 0. And this will work for any path we choose. We can come up with a sufficient collection of zigzags that will amount to the same difference. So our strategy is to go and calculate this bit, and of course we've already found this bit here, so we really just need to find this piece right here. Okay, so let's say, since what we want to find is the electric potential energy, we'll say that our final distance here is r, and we will go ahead and set our initial distance between the two charges to be infinity. So out at infinity, of course, the force will be 0. So then we've got no problem sliding this around along the arc. But remember, since we are setting the potential energy to be 0 out at infinity for exactly the same reasons we did it for gravity, it just makes sense to think about bringing the charge in from infinity. If this makes you feel a little squeamish, you can just make this equal to r initial, and then at the end you can take the limit. As r initial goes to infinity, you'll get exactly the same result. Okay, so now we've got to be very careful about this, because when we set up our integral, anywhere along here, because our hat points radially out, at any point along here, dr is going to point out. And also, because we're assuming a positive charge, the electric force at that location will also point out. So the dot product will be positive. So along any differential of motion along this path, we'll say d, the differential work done by the electric force, will be the electric field dotted with dr. Now I know that I pointed dr out. When we put in the limits, it will automatically take care of us pushing it inward. So this, since the two are lined up, this is just going to be Fe times dr. And now we can go ahead and evaluate our integral. So the total work done by the electric force will be equal to, well, initially we start at r equal to infinity, and then we end up at r dr of the electric force. Okay, quick reminder, physicists like to put the variable they're integrating over right next to the integral sign. And before you have a cow over that this is an r and that's an r, physicists know deep in their heart of hearts that you should really say something like dr prime or dr star or something like that, and let this limit be r. But we usually don't bother, because a lot of times we're using primes and stars and stuff like that to mean something else, and so the notation would get excessively cluttered. So we understand that this r is not that r, but we write it anyway. All right, so while we're at it then, we can go ahead and say that the potential energy here, because we set out at infinity to be 0, this is the same as the change in the potential energy, and this will be equal to the negative of the work done by the electric force. So this will be the negative of that integral. All right, so let's go ahead and put in. The electric force is given by Coulombs law, and I'll just go and pull all the constants out right away. So we have our minus sign. Coulombs law will give us a 1 over 4 pi epsilon naught. If you prefer to write a k, knock yourself out. Q1, Q2, and we'll be left with the integral from infinity to r dr over r squared. Well, this integral is going to evaluate to be minus 1 over r. So we'll have minus 1 over r, and we have a minus sign in front. So this is going to give us 1 over 4 pi epsilon naught Q1, Q2 times 1 over R evaluated from infinity to R. So this will be 1 over 4 pi epsilon naught Q1, Q2 times 1 over R minus 1 over infinity, and 1 over infinity is equal to 0. And if you don't like that, again, you can make that an R initial and take the limit as R initial goes to infinity if you want to be fussy about it. In any event, when we rearrange it all, we get that our potential energy function is, as advertised, 1 over 4 pi epsilon naught Q1, Q2 over R. And again, we keep in mind that we made the choice to set the potential energy to 0 at infinity. But this actually makes a lot of sense, because when you think about the issues of what the spontaneous behavior is if the charges are the same versus opposite, it works out the cleanest if we make this choice. Although it's not strictly necessary. You could add whatever positive constant you want. It's just not going to be as nice. All right, so let's go ahead and do another practical example with this. So let's say that we have two alpha particles flying towards each other. Now, an alpha particle is a helium nucleus. And a helium nucleus has a charge of plus 2e. And you can find these, say, in the core of the sun or something like that. Let's say they are both initially moving at 1 million meters per second. And they are on a perfect head-on trajectory. Now, a million meters per second seems awful fast, but compared to the speed of light, that's actually relatively not much. We'll also say that initially they are very far apart. So we'll take that as code to mean that the initial separation, we will just approximate it as infinity. And then what I want to know is how close will they get? We know that they're going to slow down because they're going to repel each other. So there will be a point of closest approach. All right. So let's go ahead and work that out. So again, we can make a table of all the forms of energy that we can think of. So we'll say final and initial. Now remember, potential energy is always expressed for a pair of things interacting via a force. But here we've got two particles. So just to keep them straight, we'll say that this is particle 1 and that's particle 2. So then we'll have a kinetic energy for particle 1, a kinetic energy for particle 2, and then an electric potential energy for their mutual interaction. So at closest approach, this would be 1/2 mv final squared, but v final would be 0 at closest approach because it's just about to turn around and go back out. Ditto here. And the potential energy here is going to be K Q Q over Rx. initially, this is 1/2 mv initial squared, 1/2 mv initial squared, and because we assumed infinite separation, the potential energy is 0. So again, same deal, just to add up the columns and equate. So we will have kq squared over x is equal to 1/2 mv squared plus 1/2 mv squared is just plain mv squared without the half. Then we're solving for x, so a little bit of cross multiplying will give us x is equal to kq squared over mv squared. All right, so we'll go ahead and stick in our numbers. So the mass of so K is 9 times 10 to the 9 Newton meters squared per Coulomb squared. Q is, since it's an alpha particle, that is 2 times the fundamental charge, which is 1.6 times 10 to the negative 19 coulombs, and we'll need to square that. Similarly, the mass of an alpha particle, an alpha particle is a helium nucleus, so it's 2 protons and 2 neutrons. As long as you're not fussing beyond a couple decimal places, the mass of a proton and the mass of a neutron are almost the same, so we'll just say it's 4 times the mass of one of them. If you look at the mass of a proton or a neutron, they're both about 1.67 times 10 to the negative 27 kilograms, and we times by 4 because the alpha particle has 2 protons and 2 neutrons as a helium nucleus. And then our initial speed was 1 times 10 to the 6 meters per second, and we will square that. I promise you, when you grind through all the units, that you do indeed get meters. We can see here this Coulomb will be squared, cancels against that. We have Newton meters squared here. Remember, so this will be kilogram. So the Newton is kilogram meter per second squared, so this is kilogram meters cubed per second squared. We lose 1 kilogram and 2 powers of meters and 2 powers of seconds, and we're left with 1 power of meters, and we're good. So let's go ahead and run this through our calculator. So we got 9 times 10 to the 9. We have 2, and we will have to multiply that by 1.6 times 10 to the negative 19. And then we will have to square that. And then multiply. There we go. We will divide by our mass. And then we'll put in our speed, square it, and divide. And yeah, that actually seems kind of reasonable. We get 1.38 times 10 to the negative 13 meters. You say, well, geez, that sounds awfully small. But for purposes of comparison, a nucleus is about 10 to the negative 15 meters across, and that's where the strong nuclear force would actually start to engage and cause nuclear fusion. So these particles won't get close enough together for nuclear fusion to occur. But this sort of process is what happens in the sun. For instance, 2 protons will occasionally just happen to be lined up perfectly enough and going fast enough initially that they do get to within 10 to the negative 15 meters of each other. And when that happens, the strong nuclear force takes over to attract them, and nuclear fusion occurs. Alrighty. In the next video, we will take a look at what happens if we have more than 2 charges to take into account, and also what if we have an electric dipole in our field. See you in the next one.